Yes, thank you for the introduction. So I'm Alexander Dijkshoorn, and I'm a PhD student at the University of Twente in the robotics and mechatronics group. And today I would like to share our work on mechanical interlocking for creating connecting electrical wires to flexible prints. First, I'll explain the challenge to you, what we're actually trying to achieve, and then I'll go to a bit of theory, fabrication, measurement method, results, and I'll close up with a conclusion. So our group mainly focuses on 3D printing with fused deposition modeling, and then we focus on printing sensors and electronics. Fused deposition modeling is the desktop method for 3D printing. So you have an extruder which extrudes a molten plastic line by line, layer by layer, to create your geometry. And this is interesting for printing sensors and electronics because it's low cost, it's very simple, and it allows for multi-material prints. So we can print up to 5 materials in one print with the same machine. So that's very interesting because most printing techniques are limited to one material because you cannot switch during the process. And this method is actually ideally suited for printing flexible structures with embedded sensing and embedded electronics in one printing go, basically. Or you can think of applications like wearables. Here you can see a soft EMG band from one of my colleagues with electrodes printed inside and with soft tactile sensors on the fingers. Or you can think of topics like soft robotics, where you can embed sensors in your flexible pneumatic actuators. However, one major challenge is still to bond the stiff copper electrical wires to your sensors in the 3D prints. And in the literature, there's a lot of solutions are proposed. So you can think of melting in some standard connectors, embedding wires or tape during printing, or applying silver paint or silver epoxy after fabrication. Or doing combinations where people embed wires and embed silver epoxy and then print on top of it to embed it. And all these methods heavily influence the contact resistance. So whatever method you pick, it will change your contact resistance for your samples. And actually, it's more difficult to do this for flexible prints because of the mismatch in material properties. And therefore, in this work, we propose to use mechanical interlocking for this. Now, what is mechanical interlocking? Mechanical interlocking is the concept where you use, instead of adhesion, you use the shape of both of your materials to create some interlocking structure. So let's say you have material A, material B, you create a shape so that they simply cannot be moved apart without tearing them, without breaking them. And additive manufacturing is really interesting for this because of the design freedom that you have. So one example, which is from the literature, is, for example, printing these metal tree root kind of structures, which extend into a polymer, which you can mold around it. So in this way, you really have a shape that locks into another shape. And this enables you to actually, this gives you the strength of the material instead of the strength of the adhesion at the interface. So in this way, you can really engineer strong connections without being dependent on adhesion, which is useful for metal polymer connections because they have poor adhesion. And furthermore, they have really different mechanical stiffness and thermal expansion properties, which can give rise to high stresses in your material locally. And by designing this properly, you can really connect these two types of materials and you can distribute the stresses to give more stable contacts. Yes. In our work, we propose for this work to do this with punctured copper tape. So we take normal copper tape, we make holes in it, we put it in the sample during printing, and when we print on top of it, the material flows through the holes and really creates this interlocking, this connection through the materials by itself. We print with standard fused deposition modeling printing, and we use standard copper tape. And during printing, we use high temperatures and a high flow rate to really make sure that the material flows through the holes. So in this cut through, we've made a sample, we've made a cut through, you can really see that the material is going through the holes in the copper tape. So it's really connecting on both sides, creating this link, which has to be broken to break the contact. And for the copper contacts, we've made a custom hole punch so that we can punch different patterns of holes to really try different designs. And we've also made wire samples. So we've made several samples with wires to compare to what is one of the most used methods where people embed simply one wire into a print. For the measurement method, we wanted to see how robust the contacts are. And for this, we simply pull on the wire to see if it works. So we have our sample, which we fix through the hole in the center. We pull on one of the contacts with a linear actuator, and we did tests with UNIAXIAL pulling, going from 0 to 12 newtons step by step. And we did cyclic pulling when we increase the force and release the force again for several cycles to see how robust this is. And during this pulling, we do a 4-point measurement and a 3-point measurement. We switch between both, and the difference gives us an indication of the contact resistance. So in this way, we can look at the contact resistance while pulling and while straining the interface, the contact. And we did this for various numbers of holes to see what the effect is of changing the hole pattern or changing the number of holes, where we clamp one of the contacts, pull on it, and then we had samples with copper tape and with wire connections. So for the results, we measured the contact resistance before pulling on a sample, and there we saw that the number of holes doesn't really seem to influence the initial contact resistance. Although for the copper tape, our contact resistance was significantly lower than for the embedded wires. Then for the pulling, you could see that from 0 to 12 newtons, you could see that initially there's a rise in contact resistance, which then seems to become stable, and after a while sometimes even goes down. For the samples with only 0, 1, or 2 holes, for a certain force, our contact would break. For more number of holes, they would stay intact, whereas the wires would also break around these values. So mechanically, for more than 2 holes in our design, it seemed to be quite reliable and also more robust than the wires. And what's interesting is that these materials have a really high resistivity. So actually, our contact resistance was, when you put it in percentages, was insignificant compared to the total sample sensor resistance. For the cyclic measurements, you could see that after a while, a stable hysteretic cycle formed. So first, you notice some drift. So we were cycling, and you notice that there's some drift in the sensor. But then after a while, you get this stable cycle where first, upon pulling, the resistance increases a bit, and then it goes down. And when you release it, it again goes to the 0 force, the 0 Newton value. And for the fracture, actually the failure mode, the main failure mode was a breakage of the TPU. But we could also see for the low number of holes, we could see the bearing of the holes. You could really see that the holes were tearing and elongating in the pulling direction. So in that case, multiple holes helps because you really distribute the stresses over the entire contact. All in all, we've shown that mechanical interlocking can be used to connect wires to flexible 3D prints, giving both electrically and mechanically robust contacts. And we strongly believe that the contacts work so well due to the mismatch in the thermal expansion of the metal and the polymer. Because what happens when you print, we print at 225 degrees Celsius, I think. Then the polymer shrinks after cooling down. The polymer shrinks a lot more than the copper, which gives this pressure on your contact. So the polymer really squeezes around your copper contacts from all sides. And this pressure, we believe, helps in improving or lowering the contact resistance, basically. One of the indications we got for this is that when we print only 1 or 2 layers of TPU on top of our contacts, then you can really see after cooling down these dimples form, like these dimples in the surface, because it shrinks a lot. And actually what we could find in literature is that Nassar et al. Did tests on electrical wires where they put them underneath the sample, inside of the sample, and on top of the sample. And really the situations, the cases where they put the wires inside of the samples gave the lowest contact resistance. So really putting your wires inside seems to be the best option for this. For future research, we're interested in also using silver paint to lower the contact resistance. And we want to study how the hole patterns and how the design of the copper tape shape influences the performance. And finally, we want to move towards applications in soft robotics and biomechanical applications. Finally, I would like to thank the EU for partially funding this work, and I'm happy to answer any of your questions. Thank you for your attention.